This is pages 3 and 4 of the Unit 8 practice test. I actually haven't done page 4, so I think that'd be a good opportunity to kind of show how I approach physics problems, how I kind of think through them, and if I get anything wrong, of course you guys can let me know. But yeah, hopefully you guys can kind of see how I approach physics problems for the first time. Starting on page 3, they basically give us like, okay, group E, they found a bunch of these measurements, like the pendulum length, the amplitude, the pendulum mass, and the frequency, and we got to make some calculations to show whether this data is good or bad. Alright, so they give us a lot of things. One thing that we can kind of do to just verify everything is just take a look at, okay, we know the length of the pendulum is 0.64 meters, and we know the frequency is going to be 1.25 hertz. We can figure out, like, using the period of a pendulum equation. So T pendulum is going to equal 2 pi square root L over G. If we plug in, so 2 pi square root 0.64 meters, and then the gravitational constant, not constant, but field strength, 9.8 newtons per kilogram, we'll find a period of, let me just check, 2 pi times the square root of 0.64, right? 0.64 divided by, is that it? Yeah, it's 0.64 divided by 9.8. I got a period of around 1.606 seconds. So if I convert this to frequency, or not convert, but if I figure out the frequency is equal to 1 over t, frequency will be equal to 1 over 1.606. If they got the length, like if they measured the length correctly, they should have gotten a frequency of 0.62 hertz. So their frequency's off. And it doesn't seem like it's off by a lot, but if we actually, now we can do the same thing, frequency is equal to 1 over period, right? You can figure out that the period is 1 over 1.25 hertz. We can figure out that 1 divided by 1.25, that's a period of 0.8 seconds. That's like half of their period, right? That's like if it's going half the speed. No, not half the speed, but yeah, it's half as slow, 2 times as slow, whatever. The point is it's off by a lot, so we can kind of make the conclusion it's bad data. For the next question, what did they mess up? What was a bad data? What was their mistake during data collection? Well, there's a lot of things they could have messed up. I think the easiest thing to mess up is just measuring period correctly, right? Like, making sure that you, oh wait, what's interesting? One thing they could have done is they only measured half the swing. I literally just thought about this, but if you have you're doing pendulum stuff or spring stuff? Pendulum stuff. If your period is back and forth and it's 1.6-ish seconds, then your, half a swing would be right around 0.8 seconds, which is what we measured. So what could be very probable is that they only measured one swing, right? So I'll just, add this here. Only measured one swing. There you go. Only measured one thing. That very well could have been the issue, right? So now number 4. This is a very interesting, not interesting, but just a cool, I guess, SCP-6 explanation question. As a mass on a spring oscillates back and forth, it loses energy over time. While this happens, what happens to the period? Explain. Everyone's gut instinct, including mine, was to say that, okay, if it's losing energy, the period is going to get longer, right? Because if initially it's starting off oscillating and then it's going to slow down and then come to a stop, the period must be getting longer and longer, right? But let's use what we know about physics and think that through. If we have, let's say initially, so for our spring, all the energy is stored as U spring. Okay, So this is at when it is, right? If you're at equilibrium, this is when it's compressed or stretched, whatever. Then at equilibrium, so we can draw like sort of the equilibrium, it's gonna have K, but then there's energy lost. So we can draw like K, but then this pie chart will be like E lost, right? E thermal, E whatever, the energy that's lost. Then at the next amplitude, we know there's going to be even more energy lost, and the rest is going to be U spring because it's all compressed. I drew the amplitude looking bigger, that's my fault. But as you can see, U spring decreased. So boom bada bing, U spring decreases. U spring is equal to 1/2 kx squared. So if U spring got smaller, your x, right, your amplitude, because that's what the x represents at the maximum there, the amplitude got smaller. But we know that amplitude doesn't affect period. It's not in our equation. Right, m over k. It's not in our equation. So that seems like it should have no effect on the period. And that is kind of counterintuitive, right? But if we think about it, like if we think about it with energy and stuff, like as you lose energy, you're gonna have less and less K, but we also know that it's gonna like not stretch as much. So it's the same idea. Less K means less speed, but you also are going less distance. So it's this reoccurring thing that, yes, speed matters, but distance also matters, and when they happen to increase at the same time, they balance out, not really cancel out, but yeah, there you go. Everything balances. Okay, I haven't done page 4. I looked at it though. I wish I didn't. I wish I kind of got the, my first, I guess, impressions here, but it's okay. Here's how, let's just go through it. So, astronauts are wanting to, have the spring system to determine their mass, but unfortunately, the spring broke. So this K, the spring constant, is different. And we got to figure out what is that new spring constant. So there's a procedure, and there's no procedure. We just have to think about what measurements they'll be making with the meter sticks, strings, set of label masses and stoppage. Okay, so we have some things to work with here. So we can figure out what is the spring constant. So there are for any experimental design or anything like this, start with your analysis first. We know we got to figure out K. What are some graphs or something we can sort of do to figure out what K is? So we have masses and we have the spring. One thing I'm just thinking is we could we can measure the period, our dependent variable, we can measure the period of that spring whenever we put in some known masses. So when we changing M. What we would expect is that when we place more and more masses, right, the period is going to get longer, it's going to take more time to oscillate, and we know from our equation it would get a square root. And then to linearize it, we would do the t squared over m. And you're like, that's awesome, how are we going to figure out what k is? Well, when you linearize t squared and m, you get the slope is 4 pi squared over k. So obviously you can then use your calculated slope. So now that I just did part B. So I guess for part B I would say, is this bleeding through? No, it's not. Make graph. And then I'll draw that. Okay, but yeah. So, what are the measurements? So going back to part A, what measurements are we going to need to make? Well, we need to know the period. So I'm going to write a little mini procedure here, but like place known mass, right, on spring, measure 1 oscillation with the stopwatch. then just graph, right? So hopefully that kind of makes sense. Another thing you could do, and now I can write this down. So period of oscillation for mass. What are we doing? Like mass as t with stopwatch. Okay. Another thing you can do is, instead of doing it like that, they actually give a string. So you can sort of, if you had a spring vertically, oh wait, would this work? Would this work? Because on the space station, right, gravity is the thing that's going to cause it to stretch. Oh, I don't think this will act. Wait, why did they give us strings? I was thinking about like sort of doing this sort of thing, the stretch, but that won't even work because we're on the ISS. So yeah, just don't worry about it. I'm not sure why there's strings. Maybe I'm missing something. You guys can let me know. Going back to 4. Oh, I just did 4. I don't know why I erased it. Hopefully you got it, or 5C I mean. Hopefully you guys saw that graph. We're just doing that sort of linearized, that linearized graph, t squared over m. So slope equals 4 pi squared over k. So then k is going to equal 4 pi squared over slope. Okay, awesome. Hopefully this isn't bleeding through. Okay, that's not bad. And then, suppose the scientist made a mistake and got a spring constant value in the calculation that was larger than the actual value. Then if they use that to calculate their mass, so they got so what's happening is they did this experiment by mistake. They got a larger k. So then how, like if they use that to calculate their mass, would their mass be larger, smaller, or the same size as their actual mass? Ooh, that's interesting. Okay, so let's think about this. I actually don't know what to say right off the bat. So here's how to approach it. If you had your spring, so I don't know, on the video they showed us, it was like something like this, and then you just place your little guy, and then it'll go back and forth. So let's say they measure their mass, and they're going to do this t equals 2 pi, square root m over k, right? So if they measured a greater mass, okay, but they're using a greater k, so just remember that. The k they're using in their equation is greater. When they hop in the spring, they're like, oh, this is less k. I mean, they don't know, but this is less k. So what's going to happen is the spring force is lower, so they're going to essentially, so spring force is lower, so they're going to accelerate less, and then they're going to have a smaller period. So bigger k leads to a larger period. Okay. And then, alright, let me actually, what I'm going to do is just kind of explain this. They're going to have, I'm going to derive an equation. So we have t squared equals 4 pi squared L over G. And then, this is pendulum, sorry, M over K. And then if we want to solve for M, we're going to do t squared K over 4 pi squared equals M. So if they're going to have a larger t, and they're going to have a larger k, so, with their derived equation, they're going to have a larger m. And that kind of makes sense, because if you think that, I'm trying to think of a way to explain this. If you have a larger k, and then it's like, you also have a large, if they think their k is large, right, they're gonna expect, how do I explain this? Like, if they have a larger k, they're gonna oscillate, right? And they're gonna find out they have a really long period. So if the k is really large, for them, they think the k is large, that must mean bigger force. So if you have a long period, right, that's gonna mean a bigger m. Because you have a larger force and it's harder to accelerate, so it's taking longer time. In reality, what's going on is there's actually less k. And because of that, if we were to make this accurate, right, if this k were not big and it was just regular, they're going to actually have less mass. So their calculated, their calculated thing would be larger. And the way I would explain that with forces is with a larger k, they would expect oh, how would I explain this? Maybe I'm explaining this wrong, but like with a larger k, they would expect less period, right? Because the force is larger. And if we think about the equation, k is in the denominator, so larger k must result in less t, because larger force, but less k leads, so less k, like the actual k leads to less time, or more time than expected. So if they have more time, they're going to think, oh, it's hard to accelerate, so thus, a larger m. Because hard to accelerate. I can't fit that on my page, but hopefully that kind of makes sense, right? Because if their k is less, they're gonna have a larger t. They're gonna put t in the equation, but when you have k here, they're putting a larger k, so that's gonna result in a larger m. When in reality, it's less k, which will result in less m. Because if you have less k, you have less force, which means less acceleration. Wait. Because you have less, so if you have more k, I don't know how long this video is, I haven't checked. This might be like 20 minutes. 17, okay, so basically as long as that. This is how dark it's in here. Oh, hopefully you guys were able to see that. I didn't notice it was that dark. But, yeah, so if you have more k, okay, I think, okay. So because they predicted it's a larger k, they were predicting less time, right? Like they would expect a small amount of time because it's a large force, and because they got a large time, what they're thinking is, okay, I have a certain amount of force, and a large time means low acceleration. So for this force I predicted, I must have a high mass. And they would get a high mass, right, just based off that equation. But in reality, so if you do like kx equals ma, what's really happening is if you have less k, you have less acceleration. So if you have less k, you have less acceleration, which would result in a greater period. Okay, I'm gonna have to think about that. So maybe I don't know, if you're still confused, you can like text me or something. But yeah, thank you for watching. I'll think about this more.